Assalamualaikum and a very good day to all students that are taking polymer technology courses. For today, we're venturing into chapter 2, which is polymer structure and properties. So for this topic, we will see how the polymer structure of each polymer will affect its property or end use of the polymer itself. So basically, in this topic of polymer structure and properties, we will underwent the outline as below. The first of all is the introduction of the polymer properties, polymer structure, and how each polymer is differ from their structure from one to polymer to another. The chemical bonding that involved in each polymer structure that develop the polymer properties itself, and then we will look into the physical properties of the polymer, and then the last one is the thermal properties of the polymer. So basically these both property have great impact on the usage of the polymer to be used in certain application and their usage. Okay, so basically polymer is a belongs to the higher molecular weight end of the spectrum. Okay, so in the following discussion, we will attempt to illustrate how the unusual properties of higher polymer are developed. Okay, so to do this, it will be convenient to consider chemical and structure aspect of polymer at three different levels. The first one is the chemical structure or atomic composition of the monomer or the primary structure. Then we will look into the single polymer chain, the secondary level itself, and last one, the aggregation of polymer chain, or also known as tertiary structure. Chemical bonding. So basically, chemical bonding, before we proceed into an extensive discussion of this aspect, we must first consider the polymer molecule operative in polymer. After all, this is the fundamental to understanding the polymer structure. So the understanding of chemical bonding that involved in each polymer is very crucial. Introduction. The electronic structure of atom determine the type of bond between the atom concerns. As we said earlier, chemical bond may be classified as primary or secondary, depending on the extent of the electron involvement. So the valence electrons are involved in the formation of primary bond. This results in substantial lowering of the potential energy. Consequently, primary bonds are quite strong. On the other hand, valence electrons are not involved in the formation of secondary bond, leading to a weak bond. So primary and secondary bond can be further subdivided into primary bond. It can be ionic, covalent, or metallic, whereas the secondary bond can be classified into dipole, hydrogen, induction, and van der Waals or dispersion forces. Ionic bond. So ionic bond is the so-called inert gas, which is the uh, neon argon have completely filled S and P outermost orbital, resulting in spherical distribution of electron. The inert gases of these element gases suggest that their electronic configuration confers stability. It is indeed observed that all elements seek to achieve this stable inert gas electron configuration. So they do this by either losing, gaining, or sharing of electron. The mutual satisfaction of the need to attain the inert gas electron configuration by this element that lose electron, also known as electropositive element, and those that gain electron, electronegative element, leads to the formation of ionic bond. To illustrate this, consider sodium chloride and ACl. Sodium with low ionization energy can easily lose the outermost 3 electrons to achieve the stable inert gas configuration. Ionic bond. Chlorine, on the other hand, with large electron affinity can achieve a stable electronic configuration by gaining an extra electron. The loss of an electron by sodium results in positively charged sodium ion, while the gain of an extra electron by the chlorine atom results in negatively charged chloride ion. The bonding forces in sodium chloride is a result of electrostatic attraction between the two ions. The ionic bonds are not common feature in polymeric materials. However, divalent ions are known to act a cross-link between carboxyl group in natural resin. The relatively nucleus of polymer, known as ionomers, contain ionic bond as will be discussed later. Covalent bond. Previous slide, we saw that the stable inert gas electronic configuration can be achieved by electropositive element through ionization. For elements in the central portion of the periodic table, ionic bonding is impossible because a large amount of energy would be required to ionize the valence electron. However, a stable electronic configuration can be attained by sharing of electron valence. Bonds formed by electron sharing are called covalent bonds. Consider the formation of methane from hydrogen and carbon. The carbon atom has four unpaired electrons in the outer electron shell, while hydrogen has one electron. By sharing electron, one of each per bond, a stable octet is attained for the carbon atom and a stable pair for the each hydrogen atom. The result is methane molecule. Okay, this is the predominant bond in polymer. Covalent bond can be single, double, or triple depending on the number of electron pair. Typical value of bond strength expressed as dissociation energy for covalent bond that commonly occur in polymer are summarized in table 1 in the next slide. Recall that dissociation energy is that the energy required to break the bond. It has direct relationship with the thermal stability of the polymer. Note also that while atoms are free to rotate about single bond, which means it is flexible. However, they still remain special, fixed, rigid for double bond and also triple bond. Table 1 do exhibit the properties of some primary covalent bond in polymer. As you can see, the type of bond and the bond length, also the energy dissociation and level, the type of bond involved in each polymer, the bond length and the average dissociation energy in each polymer is shown in the table 1. Dipole force. Molecules are electrically neutral but will have a permanent dipole if the center of the positive and negative charge do not coincide. This arises of the electron shared by the two atoms spend more time on one of the atom due to differences in electronegativity. This can be illustrated by considering a diatomic molecule such as hydrogen chloride or HCl. Because of chlorine is more electronegative than hydrogen, the shared pair of the electron between the chlorine atom and the hydrogen atom is drawn closer to the chlorine atom. Consequently, the chlorine atom has net negative charge while the hydrogen atom has a net positive charge. This diagram shows you the dipole-dipole interaction between polar molecules. You can see the interaction between each molecule are being exhibited here. Dipole forces. Any diatomic molecule in which there is a separation of positive and negative charge is said to be polar. In molecular containing more or two atoms, The polarity of the molecule is determined by the bond angle. Polar molecule therefore has a small separation of charge and this set up a permanent dipole. Dipole interact through Coulombic forces which has become quite significant at molecular distance. Polar molecules are held together in the solid state by the interaction between the opposite charges and of the molecule. The interaction forces between each molecule are called dipole interaction forces or dipole-dipole interaction, which is shown in the previous figure. This type of molecule orientation is generally opposed by thermal agitation. Consequently, the dipole-dipole interaction is temperature dependent. As we shall see later, dipole forces play a significant role in determining the tertiary structure and hence property of some polymer. Hydrogen bond. A particularly important kind of dipole interaction is the hydrogen bond. This is the bond between a positively charged hydrogen atom and a small electronegative atom like oxygen or nitrogen. The anomalous properties of water, for example, are associated with the hydrogen bonding between the water molecule or H2O. The difference in electronegativity between hydrogen and oxygen causes the bonding electron in H2O to shift remarkably to the oxygen atom so that the hydrogen may behave essentially as bare proton. This figure exhibits the hydrogen bonding between two water molecules. So the water molecule is being bonded together by the hydrogen bond. Hydrogen bond is limited primarily to compound containing nitrogen and oxygen because the small amount of size of hydrogen permit this atom to approach the hydrogen atom in other molecule very closely. For example, in spite of the similarity in electronegativity between Cl and H and N, HCl with larger hydrochloric atom show hardly any tendency to form hydrogen bond. Hydrogen bonds are relatively stronger than the dipole-dipole bond due to small size of the hydrogen ion. Table 2 exhibit the radiation interaction of energy for different type of bond found in polymer. The dipole-induced dipole is have interaction energy below than 2. When the world forces, the interaction energy is between 0.08 to 4.0. Dipole-dipole have interaction energy of below or equal to 20. Hydrogen bond have a interaction energy of below of 50 or equal to 50. Covalent bond 60 to 6000 interaction energy, whereas the ionic bond is the interaction energy between 560 to 1000. Hydrogen bonding. In polymer, hydrogen bonding usually occur between functional group in the same or different molecule. The hydrogen generally part of such molecule as carboxyl, hydroxyl, amine or amide, while the other atom in the hydrogen bond is frequently oxygen in carbonyl, ether or hydroxyl, or nitrogen in amide, urethane and urea. The hydrogen bond play a vital role in the structure and properties of polymer, particularly protein. Induction forces. Induction, every dipole has an electric field associated with him. This electric field is capable of inducing rating displacement of the reactor and nuclei in the neighborhood culture. Okay, so the result is the surrounding molecule become polymerized. Example, it will possess induced dipole. Intermolecular forces called induction forces exist between the permanent and induced dipole. Induction forces are weak and temperature independent. The ease with which molecule can be polarized referred to as polarizable varies. Every dipole has an electric field associated with it. This electric field is capable of inducing relative displacement of the electron and nuclei in the neighboring molecule. The result is that the surrounding molecule become polarized. Example forces include dipoles. Intermolecular forces called induction forces exist between the permanent and induced dipole. Interaction forces are weak and temperature independent. The ease with this molecule can be polarized referred to as stability varies. Van der Waals dispersion forces. It would be expected that the gas helium, neon, argentum, and chromium are incapable of forming any type of bonding, ionic, covalent, or even metallic. In fact, this so-called inert gas derived from the name that usually stable, which is considered to be considerable reluctant to undergo reaction. However, at sufficiently low temperature, these gases are known to condense to form solid. Similarly, for molecules such as methane, CH4, carbon dioxide, CO2, and hydrogen, they have all the valency requirement to fulfill and should in principle be incapable of forming bond. Yet, this also quickly at sufficiently low temperature, it is therefore apparent that some form of intermolecular force exists in the new and this material. Electrons are usually in constant motion to their nuclei. At any particular instant, the center of the charge of the electron cloud may not coincide with those of the nuclei. Consequently, instantaneous dipole exists in the nonpolar materials. If the orientation of the fluctuating dipole in the neighboring molecule are in a proper alignment, intermolecular attraction occurs. These all activity forces are referred to as van der Waals or dispersion forces. Van der Waals forces are present in all molecules and as we can see, they contribute significantly to the bonding of polymer. Table 2 previously showed the relative magnitude of the different interaction energies, with typical melting point for various compounds are shown in table 3. Okay. Table 3 exhibit the typical melting temperature for some substance with different type of chemical bonding. This is the type term, so you can make the comparison of the melting temperature based on the chemical bonding as shown on the left hand side, which is covalent, metallic, van der Waals forces, and last one is hydrogen. Example 1 is the tutorial in which I need you to underwent the underwent the tutorial. So and then I want you to settle the tutorial and submit it to me. Okay, so basically I already give the answer. You can go through it and give your own answer in your own words. Okay, so we venture into the next subtopic, which is the physical properties. The physical properties of polymer include molecular weight (mW), molar volume (mv), density, degree of polymerization, crystallinity of material, and so on. Some of these are discussed here in the following topics. Degree of polymerization and molecular weight. First of all, let us discuss the degree of polymerization. The degree of polymerization or DP is a polymer molecule is defined as a number of repeating unit in the polymer. For example, CH2, CH2, and is the number of repeating unit in the polymer chain. The molecular weight of a polymer molecule is the product of the degree of polymerization and the molecular weight of the repeating unit. The polymer molecules are not identical but a mixture of many species which in different degree of polymerization that is with different molecular weight. Therefore, in the case of polymer, we talk about the average value of the molecular weight. Degree of polymerization and molecular weight. Molecular weight average Suppose we have a set of value x1, x2, and x3, and the corresponding probability occurrence is given by p1, p2, p3, and so on. Then the leverage average value is defined as below. Okay, so the number average molecular weight is N1 in Ni is the number of molecule having a molecular weight M1. Then the number average property of the given mass is given by as shown in the below slide. Degree of polymerization and molecular weight. Okay, the physical properties of such temperature and mechanical properties such as strength, stiffness, and toughness depend on the molecular weight of polymer. Okay, the lower the molecular weight, the lower the installation temperature, viscosity, and the mechanical properties. Due to increased entanglement of with increased molecular weight, the polymer get higher viscosity in the state which make the processing of polymer is quite difficult. Thank you class for your time. So we end our slide here. I hope you go through your slide so that you can have a better understanding regarding this topic. Thank you so much guys for your time. Have a pleasant day and assalamualaikum.